Hmm. So, in this lecture, we will discuss Vitali's theorem. So, before proving the Vitali's theorem, we will have needed two theorems. From one is Weierstrass convergence theorem, and second is Montel's theorem. So, Weierstrass convergence theorem says if Fn is uniformly convergent on each compact subset of U, then limit is also holomorphic and their derivatives is also conformally convergent, and this will be also holomorphic on this U. And Montel theorem says if Fn is a sequence of uniformly bounded on each compact subset of U, then it admits a compactly convergent subsequence. That means uh, if Fn is a sequence if Fn is a sequence of function and which is uniformly bounded on compact subset U, then there exists a subsequence Fnk which convergent compactly to F compactly. Compactly convergence means Fn convergence to F uniformly for all compact subset of U. And note that U is open subset in Cn. So we we are proving this Vitali's theorem in Cn, not especially in C. We are proving this in n dimensions. So note that. So in this theorem, this is the one point set of uniqueness. So what is set of uniqueness? Set of uniqueness. Suppose U is a open subset. U is open subset in Cn, and A is subset of U. Then A is unique here set of uniqueness if for every holomorphic function on U, we denote a holomorphic function as a OU. This is a subset of holomorphic function on U. If every holomorphic function f on U and if we restrict f on A is 0, if and only if f is identically 0, then this set A is uniqueness in U. For example, any dense subset of U, because if this D dense subset of U and F is holomorphic on U and if is 0 on D, then we can prove using continuity F is identically 0 on A. So on U. So yeah, then the D is uniqueness, set of uniqueness in U. And second example, in C, any uncountable subset of uncountable subset of is unique set of uniqueness, because we know zeros of holomorphic function are isolated or at most countable, but if this set is uncountable and if this is the A which is uncountable and if A is 0, then we can use from zeros of a holomorphic function. If has a limit point, then if is identically 0, then obviously this is uh, a set of uniqueness. These are the example. So what is the in this lecture we will prove Vitali's theorem. So in Vitali's theorem, given that A is subset of U, and note that U is open, and A is a set of uniqueness. First, note that uniqueness, and second, uh, Fn is sequence of function in holomorphic function on U, and Fn uniformly bounded, uniformly bounded on each compact subset of U. But if we recall uh, the uh, Montel's theorem, if Fn is uniformly bounded on each compact subset of U, then there exists a subsequence which convergent compactly. But in this theorem, if we will add extra one single one condition, then we get then Fn convergent uniform compactly, and F belongs to holomorphic on U. So yeah, we will prove. So on contrary, uh, suppose Fn does not converge compactly. Fn does not converges compactly. Then there exists a compact subset of U. Uh, there exists a compact subset K of U such that f of n is not uniformly convergent on K. That means, and that means Fn is not uniformly convergent on K. That apply Fn is not uniformly Cauchy. See here, we can observe like if we discuss in sequences, an is convergent if and only if an is Cauchy. But if we discuss about sequences of function, then there will be two terms: pointwise convergent, uniformly convergent. So if sequence is uniformly convergent, then this is a uniformly Cauchy if and only if. So there is no confusion what is uniformly Cauchy and what are this. So that means here, if Fn is not uniformly Cauchy, then their fixed epsilon is greater than 0, and we can find a subsequences subsequences nk mk is comes from natural number, and zk in k, and this is the sequence because we are assuming this is not conformly on K, and this is compact. Then this because this is compact, then there exist a subsequences Z and K which convergent to Z naught, and without loss of generality, and for convenient we are assuming ZK. Yes, no, without loss of generality. So, so yeah, here assume ZK converts to Z naught. So, and such that Fnk Zk minus Fmk Zk is greater than epsilon for all k, and of course Zk comes from k. But so here we got a say subsequences f and k, f from k, like this, and we have given that fn is uniformly bounded on k. See, uniformly bounded is means there exists a real number such that fn is less than for all fn in holomorphic on U. So, and from Montel's theorem, there exist a subsequences. There exist a subsequences. We are denoting nk dash and mk dash, and fnk dash conversion to f uniformly, and fmk dash conversion to g from Montel's theorem. From Montel's theorem. So we got like this. And then because this is convergent uniformly, then and this is a holomorphic function, and from this star theorem f belongs to holomorphic, and then we can use because this is uniformly convergent, then we can exchange the limit, then f n k, sorry, f n k dash z k goes to f of z naught, and sorry, f m k dash zk goes to gz naught. Uh, so then what we got, fn k zk goes to f z naught, and fn k goes zk goes to gz naught, and distance between f z naught g z naught is equal to limit k tends to infinity. But and we assume earlier this is greater than epsilon, because this is convergent to f, this is convergent to f, then by algebra of limits their differences convergent to their differences. This is the basic. So yeah, so we got this is the their value is greater than equal to epsilon, and epsilon is strictly positive, and but we assumed a is set of uniqueness, and in this set fn convergent to pointwise some function f, no, we are not sure about function, fn convergent pointwise on a. So we got limit k tends to infinity f and k dash a is equal to limit k tends to infinity, because if fn is convergent pointwise, then their every subsequence is convergent pointwise. So I as- I am assuming this. There's no such big results. So f and k if k is equal to limit k tends to infinity f of mk dash a, and this is the, if this is from here and here, this is the value of f of a, and this is the value of g. And because from state of uniqueness f is identically g, so we get f is identically g, but we get f z minus g z naught is less greater than or equal to epsilon, and this will be true if and only if epsilon is 0. But earlier we assumed epsilon is strictly greater than 0, and which is contradiction. So our assumption is wrong. We assumed fn is not uniformly caused, fn is not compactly convergent. So fn is convergent compactly, some function f, and from Weierstrass theorem f belongs to OU. So we proved what was the Vitalis theorem says. Yeah, exactly, we proved Vitalis theorem. The let A is a subset of U which is uniqueness, and Fn is uniformly bounded on compact subset of U and convergent pointwise on A. Then Fn converges compactly to U, and F belongs to holomorphic. So some we will discuss some application of Weierstrass theorem and Vitalis theorem. So yeah, so using Weierstrass theorem, we will prove OU, which is if such that if is holomorphic on C, holomorphic on C is complete. That means every Cauchy sequence is convergent sequence. So I will use some result. So first we define CU, which is f, this function f u to c valued function, and this is continuous, and this is complete. And we define metric dfg is equal to series m is 0 to infinity 1 to the power 2m, and f minus g infinity supremum norm on km, and 1 plus. So what, so there is the one more thing we are explain we will explain compact exhaustion. So U is a compact exhaustion if km is compact subset of U, and km contains to km plus 1 interior, and U is equal to union of km, then U is compact exhaustion. So and this metric is well defined because we are assuming here supremum norm. So this value is we and because this is compact, then we get some maxima minima. So assume this will get some value m, and because this is greater than this, then their denominator is lesser than 1, and this series is convergent. So yeah, this series is convergent, so this we get some finite value, so this matrix is well defined. So what we get, tu t is complete metric space. There is one result we can prove easily. There is nothing big deal. We can take sequences of function which conversion to f, and f is continuous, then this will be complete. And there is one result, if fn is sequence of function in cu, then this is convergent in cu if and only if fn converges compactly. Compactly, that means fn convergent uniformly on each compact subset of u. So yeah, and we observe OU is subset of CU because a holomorphic function is continuous. If we show this is closed, then we are done. So if you take fn its sequences comes from holomorphic function U, and fn convergent if, but from here fn converges compactly, and then from Weierstrass theorem f belongs to holomorphic. So yeah, if belongs to you, and this is closed, and that apply OU is complete. OU is complete. So this is the best application of Weierstrass theorem. And now I will discuss application of Vitali's theorem. So suppose we will discuss holomorphic of Euler Vita function. So suppose D is a convex subset of C2 Z omega such that real Z is greater than 0. And this is convex subset of C2, and define B Z W 10 T omega minus 1 1 minus T Z minus 1. And using Vitali's theorem, we will prove this is holomorphic on D. So yeah, we will prove. So we define B delta Z B delta Z W is equal to 1 minus delta T omega minus 1 1 minus T Z minus 1 dt. This is question star. And recall, if we study basic real analysis, uh, if this function beta m n sorry, beta mn 1 to 0 t m minus 1 1 minus t n minus 1 dt is conversion. Why we are saying this integration is conversion? Because this is the improper integral, and of course m is greater than 0 and n is greater than 0, because this power could be negative and this will go denominator, and if this will go in denominator, then 0 and 1 will be point of discontinuity, and this goes infinity. So we cannot say this integral is finite. So that's why this is improper integral, and in improper integral we will we discuss about convergent or divergent. So, yeah. So and this in we know that this will be in convergent if limit epsilon goes to 0 plus 1 plus epsilon. Suppose this is function of ft, uh, a and ft dt plus a 0 plus epsilon, and this is ft, and a belongs to 0 open interval 0 1, and basically if we combine this we'll get limit epsilon goes to 0 plus 1 plus epsilon epsilon ft dt, and if we replace, then limit n tends to infinity, sorry, here on 0 minus, then and epsilon goes to 0, then n tends to infinity 1 minus 1 by n, here minus 1 by n ft dt. So I will use this result later. So, yeah, so we had b delta z is equal to 1 minus delta delta t omega minus 1 1 minus t z minus 1 dt. So because yeah, so because if t belongs to delta and 1 minus delta, then 0 and 1 this not belongs this. So here log t is defined and log 1 minus t is defined, because if here 0 is, then log 0 is undefined, because log 0 is minus infinity, so undefined. So if there will be function undefined, then we will remove this point. So yeah, here this is the function, and so now I will prove b delta z omega is holomorphic on D. So how can we prove? So we observe, we can write t omega minus 1 1 minus t z minus 1 is equal to e log t omega minus 1 and what 1 minus t z minus 1 is equal to e omega minus 1 log t plus z minus 1 log 1 minus t, and if we can, then we can write as a k is equal to 0 to infinity uh, omega minus 1 log t plus z minus 1 log 1 minus t to the power k factorial k. That means this series convergent uniformly to this function, and that imply this convergent uniformly on compact subset, and that means convergent compactly. So because the we proved the sequence convergent uniformly, so if you take integral, then this will be convergent uniformly to this function of integral. That means, yeah, we can write easily. We define P in Z W is equal to K to 0 finite 1 minus delta yeah, what, omega minus 1 log t plus z minus 1 log 1 minus t to the power k upon k factorial. And because this we proved earlier, this sequence convergent uniformly to function t omega t to the power omega minus 1 1 minus t z minus 1, then this convergent uniformly 1 minus delta to delta uh, compactly convergent, we can say compactly convergent 1 minus delta to t omega minus 1 and 1 minus t z minus 1 dt. And so yeah, this convergent to b delta uniformly, then from Weierstrass theorem b delta is holomorphic on U. So now I will prove using the b delta b is uniformly convergent. Sorry, b is holomorphic. So our mm, so yeah, so we got b delta z omega zw 1 minus delta t omega minus 1 1 minus t z minus 1 dt is holomorphic on D. So we put delta is equal to 1 by n. And now I will not prove these things. So you can prove. I will write just b1 by n z omega is uniformly bounded on K, which is compact subset of C. This is very basic proof. We can use inequality of integral and some inequality of uh, smaller value of the power. So this is very basic proof. So and b1 by n z omega is pointwise convergent on D, and this is also very basic to prove. So you can prove. So what we get convergent, and this convergent pointwise to B. So what we get b1 by b1 by n is uniformly bounded on each compact subset of D, and second b1 by n or z or w is pointwise convergent on D, and D we can take A is D, and this is the seat of uniqueness, trivially seat of uniqueness, and from Vitali's theorem this is uniformly convergent, beta 1 by n compactly convergent, sorry, compactly converges. And then from Weierstrass theorem, beta is holomorphic on D. So yeah, that's it.